Hello and welcome to the inaugural demonstration/tutorial for Isolde, my new toolset to aid the often fraught task of modeling into low-resolution data. Isolde stands for Interactive Structure Optimization by Local Direct Exploration and is based upon two key design philosophies. Number one, at low resolution, high-quality visualization is critical to making sense of what can be a very complex environment. Hence my choice to work within Chimera X, one of the best and most flexible molecular visualization packages I've ever seen. Number two, as much as possible, the model should behave like a real molecule. You'll see what I mean by that as we go along. As my demonstration, I've picked on 4LJZ, a 3.6 angstrom structure of the E. coli RNA polymerase. I should stress that I chose this more or less at random, but specifically because its validation metrics are very middle of the road for a structure of this resolution. But before we get to that, let's look at how to get Isolde itself. If you are using a Linux machine with a good recent GPU, then after installing the Chimera X application, then simply navigate via the Tools menu to the Chimera X toolshed and install the Clipper and Isolde plugins. Clipper is a backend plugin which doesn't add any new menu entries, but after installation, Isolde can be found under Tools, General, Isolde. Support for Windows and Mac operating systems will come in due course. The Clipper plugin is a Chimera X adaptation of Clipper Python, the new Python interface to Kevin Cowton's wonderful Clipper library for efficient handling of reciprocal space data and symmetry. It has native support for map files in MTZ format and provides the now classic visualization modes for crystallographic datasets, as well as a few new tricks. This is a work in progress and still in need of some optimization. One big caveat is that the symmetry contacts are currently visual aids only. They do not yet take part in simulations, although I plan to implement this in the future. Okay, now that Isolde is installed, let's fire it up. Go to Tools General Isolde and wait a few seconds for it to initialize itself. It appears as a new floating widget. If I'm on a machine with dual screens, I like to keep this on the second display, but for now we'll just drop it into place on the right. It starts up by default in crystallography mode. Other options exist for EM maps or free simulations, but in this case all we have to do is click the Initialize Model MTZ combo button and choose an MTZ file containing map amplitudes and phases. Eventually Isolde will have the ability to calculate its own maps, but at this stage I can only guarantee success with maps generated through Phoenix.maps. One big caveat here. Due to the aggressive way in which the Isolde simulations sample the maps, it is very important to ensure that they are generated with the free reflections excluded. This is not the default behavior of Phoenix.maps, so you will need to set it manually via the Phoenix GUI or in the Phoenix.maps configuration file. Loading the maps has triggered Isolde to promote the atomic structure into a fully fledged crystal structure with live symmetry and map display. The MTZ file I'm using contains three maps, a standard 2FO-FC, one with a sharpening B factor of 80 angstrom squared, and of course the FO-FC difference map. I find it useful to set the sharpened map to a solid transparent surface at a moderately high contour to provide detail, while the unsharpened map is left at 1 to 1.5 sigma to show the overall envelope. While exploring, I also find it useful to set the difference map to a solid opaque surface to make potential problem regions really stand out. The big green blob here, for instance, is a zinc ion with a poorly refined B factor, about 200 square angstroms out of step with the surrounding coordinating cysteine residues. In a large structure like this, you'll notice that scrolling is a bit jerky with the occasional long pause. The slow frame rate comes from the overhead in determining which atoms fall within the current focal region, while the pauses occur when a new symmetry molecule comes into range and is automatically cached. These delays are almost unnoticeable in smaller molecules, and should be reduced dramatically with further optimization. All remodeling within Isolde is currently done in the context of interactive microsimulations, typically of no more than a few hundred residues. Under default settings, the current atom selection will be expanded to complete residues and extended to N and C termini by 3 residues, and then further expanded to include all residues with atoms approaching within 5 angstroms of these. These will become the mobile atoms, while a further shell of residues will be simulated but fixed rigidly in space to provide context. As far as the simulation is concerned, any atoms outside of this region simply don't exist. A very important part of my design philosophy for Isolde is the provision of constant real-time feedback on progress. An example of this is my mapping of Rama Chandran statistics to the color of the alpha carbon on each protein residue. Throughout simulations, these update a few times per second, showing outliers as dark red, marginal residues as yellow-orange, and happy residues as green. The meaning of my statement about the model acting like a real molecule should now become clear. The major advantage of working in the context of molecular dynamics simulations is that impossible, or even highly improbable, conformations are simply disallowed by the environment. When you tug on an atom, it and all its mobile atoms react and adjust according to both bonded and non-bonded interactions. Clashes, that is, atomic overlaps, are fundamentally impossible, and electrostatically unfavorable interactions will push themselves apart. While it can be fun to tug directly on an atom with the mouse, in practice it's often not particularly useful since you can only ever pull in 2 dimensions. In most cases, you're going to want to use the tools over on Isolde's Rebuild tab to perform common tasks. Here, for example, I'm playing with the rotamer tool. Every rotameric residue within the structure can be individually targeted to a specific rotamer. These restraints will remain active through all future simulations in the Isolde session, but I have not yet implemented an interface to save them across sessions. While ultimately nothing substitutes for going through the entire structure end-to-end at least once, it is of course important to have tools available to pinpoint major problems as quickly and directly as possible. Over on the Validation tab, you'll find 2 such tools, the Peptide Bond Checker and the good old Rama Chandran plot. Not all cis-peptide bonds are wrong, of course. These cis-prolines are clearly supported by the data, but as a rule of thumb, a non-proline cis-peptide bond should only be suspected if unambiguously supported by both the data and the surrounding steric environment. A cis-peptide bond in a poorly resolved and clearly flexible loop like this is simply wrong and needs to be corrected. Peptide bonds that are more than 30 degrees away from either cis or trans are also vanishingly rare in reality, and like cis bonds are flagged in the now standard fashion pioneered by the Richardson lab behind mole probity. I'm not going to fix these particular cases yet. It's probably better to wait and see if my first round of refinement will improve the local density. But here's a nice case that's trivially easy to fix. Looking at the density alone, one could be forgiven for thinking it fits fine, but knowing what we know about the true prevalence of non-proline cis bonds and looking closely at the local environment, we can say with some confidence that it's wrong. Back over on the Rebuild tab, you'll see a flipped cis-trans button near the top, which is enabled whenever any atoms from a single mobile protein residue are selected. Clicking this will flip the peptide bond N-terminal to the selected residue. We can immediately see from the C-alpha colors that fixing this peptide bond has had the added benefit of improving the Ramachandran status of the adjacent residue. When we're done, clicking the Save Changes button commits the adjusted coordinates back to the master model. If you don't like the changes you've made, then you can always click Discard Changes to try again. Let's have a quick look at the Ramachandran plot, also available over on the Validation tab. Unlike others that you may be familiar with, this implementation allows you to choose whether to plot all the residues or only those you've selected. When the simulation is running, the plot will show a live representation of the mobile residues. Like in the peptide bond checker, clicking on any point in the plot will take you to the corresponding residue. Before we go any further though, it's generally a good idea to give the entire structure a good settle and re-refinement and generate some fresh maps. This serves multiple purposes. First, it relaxes out any truly bad clashes which can generate energies of millions of kilojoules per mole, which would otherwise crash any simulation. Second, it tends to fix many small errors on its own, and reduce the ability of big errors to hide in collections of lots of small outliers. Third, it lets you choose a nice conservative refinement strategy to reduce the likelihood of overfitting the data. I'm not going to lie to you though, preparing a structure of this size for simulation currently takes a good 5 to 10 minutes, and you'll want to give it at least half an hour or so of settling before saving the coordinates. Now would be a good time to go and grab a coffee. Refining the result in Phoenix is an overnight job, so it would be a good idea to save this until the end of the day. Coming back and looking at the results after refinement, you might be forgiven for feeling a little disappointed. After all, R3 has gone up by a full 3%, while Ramachandran outliers have increased by almost 2%. I would argue that this is actually one of the strengths of Isolde. By refusing to force-fit atoms with a little clash or badly strained bond here and there, it forces errors out into the open where they can be found and corrected properly. Before we get into a few of those, here's a quick view of the benefit of this initial settling. This fairly weakly resolved region was clearly significantly displaced from its density in the initial coordinates, but the MD settling has made short work of the bulk shift needed to get it properly into place. Now here's a good example of a fairly common problem in models of this resolution. A stretch is being built out of register, that is, with residues shifted along the chain from where they really belong. The signs of this can be surprisingly subtle, and if viewed in isolation are easy to miss. But when we start to add up all the oddities along this stretch, it becomes clear that something substantial needs to be done here. This case is characteristic of most that I have seen. A relatively short secondary structure element flanked by two weakly resolved loops. The short length of the well-defined structure makes it easy to misassign side chains, while it is all too easy to slightly over or underpack the loops to get back into the correct register on either side. In this particular case, the error traces back to a homology model used to build an earlier version of this complex into 11 angstrom EM data, and has carried through to most of the 50 structures of the same complex published since. I should note here that I have alerted the author to this and other issues I found, and shared my final refined coordinates. So how to fix this? If you were using a traditional building environment, you would probably delete the loops, reassign the side chains according to the new register, and then rebuild the loops residue by residue. Instead, we're going to use my new favorite tool to simply shift the whole stretch in one short simulation. Right now, I'm defining a big enough selection to cover the problem region using a handy Chimera X feature. If you select an atom using Control-click or Control-Shift-click, then pressing the up arrow will extend this to the whole residue, and pressing it again will cover the entire secondary structure element or loop. Now we have the simulation running. The first step is to define the region that actually needs to shift. The only limitation is that this should be a single continuous peptide chain. This can be handily done using the tools revealed by clicking the Register Shift dialog button on the Rebuild tab. Next, we want to tell Isolde how far we want the stretch to shift. In this case, inspection makes it fairly clear we want to shift 2 residues towards the N-terminus, so let's dial up -2 and press Make It So. What's actually happening here is that the heavy backbone and alpha carbon atoms are attached via soft springs to points traveling along 3D splines, connecting them from their starting to final target positions. Shifting them in this way avoids all generation of clashes and allows the surrounding environment to adapt to the new reality. When it's done, don't forget to click Release to remove those spring restraints. We can see the tyrosine residue here is settled happily into the large positive density blob previously occupied by serine, but a few other bulky side chains are in need of a bit of remodelling. For the most straightforward tasks, you can simply drag them with the mouse, but in most cases it's easiest to use temporary position restraints on key atoms to precisely set the target location. The Position Restraints dialog is found at the bottom of the Rebuild tab. By default, it restrains the selected atom to its current location, but what we want to do here is select Axis Position from the drop-down menu. This will create a restraint between the atom and the current position of the XYZ axis in the middle of the screen. In most cases like this, you will want to remove the restraint once the atom is in position to allow it to settle naturally. Up here at the C-terminal end of the problem stretch is a smaller but also quite classic problem often seen at this resolution, a dipeptide flip where 2 consecutive side chains are each pointing 180 degrees away from their true orientation. This is also easily fixed with a couple of temporary position restraints. With the simulation paused, select one atom from each side chain and add a restraint approximating its new position. Then start the simulation and clear the restraints once the flip is complete. This arginine residue has not quite managed to extend out into open space after the register shift, and is blocking the adjacent valine sidechain, creating a Rama Chandran outlier. This could probably be solved with a simple quick tug using the mouse, but here we may as well dial up a suitable rotamer. Scrolling through the list of alternatives, we see the one with the second highest prevalence looks like it will make a nice salt bridge, so let's put it there. Setting the coordinates there directly would cause a clash, but setting it as a target allows both arginine and acid to settle together. After that, resolving the valine Ramachandran outlier is a simple peptide bond flip achieved in much the same way as the cis-trans flip I demonstrated earlier. In the interest of time, I'm going to skip past the remaining similar rearrangements of this segment and just show a before and after comparison of the original and final refined coordinates with maps generated using the complete reflection set. Here's a far more subtle case of a register error that is nearly invisible in the original coordinates, but has been made clear by the uncompromising nature of the molecular dynamics environment. This stretch of beta strand is out of register by one residue. In the original coordinates, everything has been compressed and twisted slightly so that all residues are in density, but our earlier equilibration has pushed the C-terminal end well out of density, making it clear something is wrong. An additional argument for a register shift here is the implausible placement of a lysine residue between a lysine and arginine on the adjacent strand. This sort of odd-numbered shift in a beta strand is perhaps the most difficult register shift to accomplish in a molecular dynamics simulation, since it involves flipping all residues around the backbone in a quite hindered environment. As you can see here, it doesn't quite make it on its own, and needs a little help from me to do the final flip. In future, I plan to add a final polishing step to improve the convergence of side chain positions. As before, here's a comparison of the unmodified original coordinates and maps to the final refined solution. As I said earlier, looking at the original coordinates, it would be entirely understandable to miss seeing the problem, since it honestly looks like a reasonable fit to poorly resolved data. In this case, I would argue that it is the molecular dynamics environment rather than the visualization that played the biggest role in bringing the error to light. As well as the examples I've shown, I've spent roughly 2 days working through the structure from end to end, fixing numerous smaller scale issues as I found them. At that stage, I find it best to avoid spending too much time on the most weakly resolved sections. It's far more productive to fix all the obvious problems in well-resolved regions first, then tackle the harder regions in the improved maps yielded by re-refinement. At this stage, it can be helpful to dial the temperature down to absolute zero, so the only movement arises as a result of your interactions. In poorly resolved loops such as this one, there is still little substitute for playing around until you find a solution that both fits the map and is energetically favorable. In future, I hope to add some more sophisticated conformational search algorithms for this task. The loop is clearly still not perfect, but at least there are no more bad Rama-Chandran outliers, and the fit to density is reasonable. Of course, one must always keep in mind that density like this is the result of an ensemble of states from what is clearly a flexible loop, so no single natural conformation can give a perfect fit. After working through the remaining outliers on the Ramachandran plot and performing a final refinement in Phoenix, here are the validation statistics. In general, there's a clear improvement in stereochemistry, with the overall mole probability score reduced from 3.05 to 1.82, and the maps for the most part look greatly improved. Yet the R factors are even higher than before, and we actually have slightly more Ramachandran outliers than there were in the published coordinates. Part of the explanation may well lie in a different choice of TLS groups and more conservative refinement on my part, but this leads me to a discussion of the things that Isolde can't do, yet. First and foremost, Isolde can't perform miracles. This dataset contains a number of exceedingly poorly resolved domains like this one, where the starting model is based on weak homology with all the problems that entails. Isolde can take you a long way when you either have a good starting model or at least the occasional clear signpost in the data, but when neither of these is true, then it's probably not going to help you much. This is not necessarily a bad thing. This sort of behavior at least gives you a clearer picture of which regions are most and least trustworthy. Given that there are now 51 deposited datasets for this particular target, the best approach would probably be to look through these to see which, if any, have better data for these domains. To aid in such an approach, in future I plan to add functionality to provide external reference model restraints, as well as the ability to incorporate other sources of external data such as evolutionary couplings or cross-linking information. Ultimately, of course, we reach the point where nothing can compensate for the need for better experimental data. In such cases, perhaps the best we can do is return to the lab to see if the most problematic domains can be captured in isolation. Isolde has been made possible by the help and support of a great many fantastic people. I'm developing it in the lab of Randy Reed at the University of Cambridge, with funding from the Wellcome Trust and affiliated to the Phoenix Consortium. The graphics environment is a fantastic work of the ChimeraX team, headed by Tom Ferrin at UCSF. The molecular dynamics library, which may as well have been purpose-built for my task, is OpenMM from Vijay Panda's lab at Stanford. Support for crystallographic data comes from Clipper, the work of Kevin Cowton at York, and the Clipper Python adaptation, which is a joint product of CCP4 and CCP-EM. I hope you found this demonstration useful, and I'll be back with more updates in the future.